Let's continue in our correlation and regression practice lab. Earlier in the lab, we ran a correlation test to look at the association between the hours spent playing violent video games and children's aggression. Now we're going to move into the regression part of this lab. Regression is simply an extension of correlation, except instead of just looking at the association by itself, we begin to make predictions. So in this part of our lab, Vivian now wants to predict children's aggression level, and that's our dependent variable, using time spent playing violent video games as a predictor. So that's our independent variable. Using SPSS, she runs a simple linear regression analysis, and the output is provided below. So remember, of course, that your independent variable is said to predict or cause your dependent variable. In this study, this is a correlational analysis. She is not experimentally manipulating the independent variable in this study. Therefore, we're simply looking at a correlation. We cannot infer a causation based on this, but that doesn't mean we don't have a theory. But that's why we use the language predicts instead of causes. So if we were to write this study up, we might talk about video game use as a predictor of aggression, but we would not say as a cause of or it increases aggression because we have not established causality. So here the independent variable is hours spent playing video games is causing, theorized to cause aggression. There we go. So let's go ahead and take a look at this analysis. The first table in a regression analysis is the model summary table. Now this is going to look a little bit like the output we saw in the correlation analysis. Let's go back up and take a look at that so we can see the comparisons. So I'm going to scroll back up to the correlation analysis. Up here we took a look at the correlation coefficient itself and the significance of that correlation. So the correlation coefficient was 0.494, and it was significant at 0.005, or p is less than 0.01, as that would be the next highest standardized cutoff point. So this is what we saw before. Let's see how this relates to what we see in our regression analysis. And we should see some similarities because this is simply an extension of essentially the same analysis. So model summary table. Let's take a look at this. Model 1. So this is a simple linear regression. We only have one predictor. It's not a hierarchical regression. So we just have one model we're looking at. And the first thing we take a look at here is R. Okay. The R is 0.494. That should look familiar, right? We looked at the correlation, 0.494. Earlier we said R is the symbol for correlation. So that's exactly what's going on here. Now technically, this is the correlation between the predictors and the outcome, right? The predicted values and the actual values. Because there's only one predictor variable, it's exactly the same as the correlation between these two variables. If we had a more complicated regression model with more predictors, this would have a slightly different meaning. Well, I should rephrase that. This wouldn't be the correlation between any one of those variables and the outcome. It would be the correlation between the predicted values and the outcome, kind of the variables taken together. Next, we have the R squared. Okay, so we have R and then R squared. So the R squared is 0.224. And how do you get the R squared from R? Well, you take R and square it. So 0.494. To find the square of a variable, we would times it by itself, times 0.494, gives us 0.244036, and they round that to the hundreds place, so 0.244. So you find the R and you square it, and that gives you the R squared. Over here, we have the adjusted R squared. We're not going to get into that. We're going to keep things a little bit simple, but this has to do with it accounts for potential chance in the predictability of the model. So here we're just going to focus on the R and the R squared. So the R squared is 0.244 and the R is 0.494. The R tells us about the strength of the association. The R tells us about the shared variance. So when you square the correlation, this tells you the proportion of the variance that is shared between these variables. Or put differently, this is how much of the variation in the outcome, or violence, aggression, well, violent aggression, aggression in the child can be explained by the amount of time they spend playing video games. Okay, so what does this tell us? Okay, so the R square is 0.24. Okay, I'm going to go ahead and round to the hundreds place. The R square is 0.24. This means that time spent playing violent video games explains 24% of the variation in children's aggression. Okay, that's what that means. So to convert a decimal to a percent, you move the decimal place 2 places to the right and add the percent sign. So an R square of 0.24 means that 24% of the variation is explained. The strength of the association is 0.49. R square is 0.24. Okay, let's go ahead and move down to the next table. This is the ANOVA table. The ANOVA table tells us about the predictive ability of the overall model. This is going to tell us whether the model produces significantly better predictions than those which would be based solely on the mean. Okay, so let's take a look. We're going to zero in specifically on the significance value right here, which is 0.005. That should look familiar. Where have we seen that before? Back up on a correlation table, the significance is 0.005. So what this analysis is, it really is just sort of repeating the correlation test we did before, although it's presenting the information in a slightly different way and allowing us to create a regression equation which will allow us to make predictions. So the significance value is 0.005. So what does this tell us? Right? So the ANOVA statistic is significant at p is less than 0.01. Okay, so 0.05, that's the next highest cutoff point, which means that the model produces better estimates than those based solely on the mean. The model is useful. Okay, that's basically what this comes down to, is this model is helpful. It's giving us information we wouldn't otherwise have. If this value is not significant, then you would not move forward and use the model. It would tell you that the predictor you have or the set of predictors you have are not giving you useful information. Finally, we have the most interesting part of the output, which is the coefficient table. And this gives us the information we need to write the equation of the model. So using the coefficient table, write the equation of the regression model. So how do we do this? Well, it begins with y equals, okay, y equals, if you think back to maybe some of your earlier education, you might be familiar with the equation y equals mx plus b, which is sort of the standard equation of a line. And b is the slope intercept, m is the slope, and then x is your independent variable, y is your dependent variable. So to get the outcome, you would take the some predicted value, multiply it by the slope, and then add the slope intercept. What we do is going to be very similar to that, except the b goes in the front in this convention, and then the x goes in the back. If you had multiple x's, you would have them represented in the equation as well if you had multiple predictors. Okay, so y equals, so it's going to be the slope intercept, and we're going to find that right here, 3.028. I'm going to round that to 3.03. Okay, so y equals 3.03. This is a positive coefficient, so 0.39 is our slope. So I'm going to do plus. If this were a negative slope, this would be minus 0.39, again rounding to the hundredths place, times x. Okay, so y equals 3.03. That comes from right here. That's our slope intercept, or the y-intercept. Okay, and then this is our slope right there, 0.392. So let's talk about what this means. We'll get a chance to work with this a little bit. So in the regression analysis, the y-intercept is 3.028 or 3.03. What does this mean? So in a linear equation, the slope-intercept is the value of the dependent variable, the value of y, when x is 0. Okay. So in this case, x is the amount of time spent playing violent video games. So this is the predicted value of y when x is 0. So how would we get that, right? So I'll show you how this works out mathematically. So let's pretend that x were 0. We had a situation where a child was playing 0 hours. So I'm going to take the x and replace it with a 0, just like that. So it's the exact same equation, but I've taken out the x and put a 0 in. So let's suppose the child spent 0 hours playing violent video games. Right? So how do we solve this equation? Y equals 3.03. Remember, order of operations, you would multiply before you would add, plus, what's 0.39 times 0? Well, anything times 0 is, of course, 0. So y equals 3.03 plus 0, or y equals 3.03. Okay. So when x is 0, y is 3.03, and that's the same as this right here. I just rounded it. So that's what the slope-intercept is. It's the expected or predicted value of y when x is 0. What does that look like visually? Right, let's go back up to the graph. Remember when we graphed these data? Right up here at the top, and we kind of came up with the line we kind of thought was going along here. Well, this is saying that if violent video game use are 0, then the expected regression should be 3. It should be right here. So it's saying this is the slope-intercept. So the line we drew before would be a little bit off. Maybe it would look more like this. But that's our slope-intercept. That's what we'd expect it to be. If you take a look at the data, it's a little above the line that we kind of drew freehand here, but it's on point. It's certainly consistent with this, right around here. So if there's no video game use, we'd expect the kid to have kind of this level of aggression of a 3, right? If this were giving us a value way up here, we would know that something was off. Okay, go on back down to our item here. So that's how you would kind of work out that slope-intercept. So what does this mean? Okay. Right. If the y-intercept or slope-intercept, same idea, is 3.03, this is the expected value of y when x is 0. In other words, if a child plays 0 hours of violent video games, we would expect him to have an aggression level of 3. Okay, so that's basically what that means. That's sort of the average level of aggression for a kid that's not playing these types of video games. Okay. The significance level of the predictor is 0.005. Okay, so this is the slope-intercept we're talking about. What about the predictor? Okay, so we know that the slope is 0.39. The slope of this predictor x, okay, is 0.392 or 0.39. What about the significance of that predictor? Well, the significance is 0.005. Because it's a simple linear regression model, there's only one predictor that is going to be the same as the ANOVA significance from that table, and the same as the significance from just a correlation test right here at 0.005. If this model had more predictors in it, maybe we had the child's age and gender and video game use, then it would look a little bit different. That would be the significance of the overall, this would be the significance of the overall model, and then you would have a separate significance level for each individual predictor. So in this case, we're looking at this significance level right here, 0.005. That's less than 0.05. So that means that this predictor is a significant predictor of the dependent variable aggression. So let's go ahead and make a note of that in our write-up. The independent variable, hours playing video games, is significant at p is less than 0.01 or 0.005, a different way of representing that. This means that video game use is a significant predictor of aggression in children. There we go. So that's basically what that's telling us. If this were over 0.05, could be 0.05 exactly, I should say if it's at or over 0.05, then that means that this is not a significant predictor and it's not a useful model. Since it's just one predictor in the model, these are going to be consistent. So you shouldn't have a situation where this is different from this, which is different from the correlation test if you only have one predictor. If that's going on, then there's probably some kind of mistake in how you inputted the data around the analysis. The unstandardized beta coefficient for the predictor is 0.392. What does this mean? Okay, this is a mouthful. Unstandardized beta coefficient. Okay. So the slope of the line associated with this variable is called the beta coefficient. So that's what this b right here is. Okay, beta coefficient. So so we have the standardized beta coefficient and the unstandardized beta coefficient. So the unstandardized beta coefficient is 0.392. So when it says unstandardized, okay, that means we're looking at this column rather than this column. The unstandardized beta coefficient is in the original units, hours. So it is very useful to use the unstandardized coefficient when the unit is meaningful. So we could talk about, the more hours if you play 1 more hour, this is the result. If you play 3 more hours, this is the result. The standardized beta coefficient basically converts this into z-scores, or standard deviation units. So this would be saying 0.49 standard deviation hours produces some sort of outcome, or relates to some kind of outcome. This is in the raw unit, so this is going to be more meaningful. So this is simply saying that we're looking at the unstandardized beta coefficient, 0.392. What does this mean? Okay, so what does it mean that this value, which is the same value we have right here in our equation, oops, it likes to highlight that, doesn't it? There we go. Right, same as this. What does this tell us? This is the slope. Okay, so if this is the expected value when x is 0, 0.3, or 3.03, right? Well, x is not always 0, right? So not all of the kids played 0 hours. Some of them played more hours. Remember our histogram up here at the top? So some kids, sure, they played 0. And so for these, we would expect the aggression level to be 3. But some kids played more, 3 hours, 5 hours, 6 hours, all the way to 10 hours. So what's the expected level for a kid that plays 10 hours? What about 11 hours or 6 hours, right? This is what this information is telling us. We start with this as our baseline, and then we add more based on how many hours they're playing. Scroll back down here, bear with me. Okay, so for each additional hour, and because we're talking about the unstandardized beta coefficient, we're talking in hours, right? Hours. Their aggression level is expected to go up by 0.39. So if they play nothing, no violent video games at all, 0 hours, they're expected as 3. For every hour they play a week, they're expected to have an aggression level go up by 0.39. Okay, so let's write that down. Okay, for each additional hour of violent video games a child plays, his aggression level is expected to increase by 0.39. Okay? In other words, a 1 hour increase in violent video game time is associated with a 0.39. What are the units? What are the units of the dependent variable, aggression? Right, so here we have something very meaningful, hours. Here, the units are sort of this ranking that they came up with, scale of 1 to 10. So it's not, the number of times they got in a fight, the number of times they talked back to their parents or something like that. It's kind of a sort of an ambiguous unit. So when that's the situation, we can just simply use the word unit. a 0.39 unit increase in aggression. So you could have said a 1 unit increase in violent video game time. That would still be accurate. But I like saying 1 hour here because we have a meaningful unit. This is going to make a lot of sense to our listener, to our reader. But here, the unit's a little bit, a little bit vague. A ranking, what does that really mean? So that's why I use the unit language here. Okay. So 1 hour increase in violent video game time is associated with a 0.39 unit increase in aggression. So just to help you make a little more sense out of this, I want to show you how this would work in an equation before we jump here into the end. So I'm going to do here. All right, so I cleared out the work I did here earlier. And let's try this with a different value of x. So before we tried it with 0, and that's how we sort of derive this slope-intercept. But let's pick a different value. Okay, so we know what happens if they play 0 hours of video games. We expect to have an aggression level of 3. What happens if they played, let's just say, 5 hours? Okay, so how would we work that out? Okay, so of course we keep the y equals, slope-intercept is the same, plus, and then our coefficient is 0.39. That's our beta coefficient. And now we're going to replace x with a 5. Okay, so we're figuring out what the predicted value would be if the child played 5 hours a week of video games. So y equals 3.03 plus, now we'll have to work out this product, 0.39 times 5, so 1.95. We're going to go ahead and put this right here, 1.95. Okay, so this is how much more violent we expect them to be, or more aggressive. This is how much more aggressive we expect them to be, roughly 2 units more, because they played this 5 hours a week of video games relative to playing none. Okay, so now the expected value is 3.03 plus 1.95, 4.98. Okay, so 4.98. Okay, so the predicted value has gone up from 3.03 to 4.98. Let's come back up to the scatter plot we did before. So earlier, we looked at our slope-intercept over here, and I'm going to erase this line that we made earlier because this is kind of just eyeballing it. And let's take a look at what that line would actually look like. Let me get rid of that here. Okay, so we know the slope-intercept is 3.03, right? Based on our coefficient table, 3.03. So let's go ahead and put that up here. Okay, so let's see here. So if 0 hours of playing is going to be 3.03, so right about there. I'll use x's to differentiate from the actual data. And if they played 5 hours of video games, we came up with 4.95, which is going to be just about here. Okay. Now we can get a sense for what this line would look like. Why don't we plot one more data point? Let's plot a 10. Let's see what we would predict the value to be if they played 10 hours of video games. So I'm going to erase all this. And we're going to try the same thing again with x of 10. Okay, get rid of the rest of these little dots here. Okay, there we go. So let's run this equation again. Okay, so now let's suppose we have y equals 3.03 plus 0.39 times 10. Okay, so this is a predicted value of 10. 10 is the hours spent playing video games. So if they spent 10 hours playing video games, then the predicted value, or y, of aggression should be 3.03 plus 0.39 times 10. So 0.39 times 10 is going to give us 3.9. So this is sort of the expected increase in their aggression level relative to playing no hours of violent video games. So we add 3.03 plus 3.9 gives us 6.93. Right there. So if they play 10 hours of video games, we expect aggression of 6.93, or just under 7. So let's go up and put this on our scatter plot. So 10 is going to work out to just under 7, which is going to be, get that guy in the way right there. I'll put an X right about there. So if we were to connect these three X's, okay, this, well, let me just do it again. I kind of missed that last X there. If we were to draw a straight line through these X's, this line represents our predicted values, or what's called a regression line. Right? So we got this line using that regression equation. This is the regression line. So now we can look anywhere on the x-axis and determine where we would expect the child's aggression to fall based on these data. So if they played 8 hours of violent video games, we would expect them to have an aggression level of roughly 6, right? 2 hours, maybe a little less than 4. So now anywhere on the x-axis, you can make a prediction based on the y-axis. So this is a visual representation of that equation, right here. So this is the equation of the regression line, and that's a visual representation of that equation. What we did is we inputted x values and we calculated y values to come up with these actual data points. Now, what if the child played 20 hours of video games? Let's talk about that. I'm going to go down here, go back to our equation. So what I'm going to do, I'm going to take out the 10. All right, get rid of that. I'm just going to get rid of this part of the equation. Okay, so I've taken out the x value of 10, and let's put in 20. So let's see what happens if the child plays 20 hours of violent video games per week. So 0.39 times 20, 7.8. So this is what we would expect to add in terms of their aggression. So now we would have 3.03 plus 7.8 gives us 10.83. Like that. So if we were to go back up, so just under 11, let's say. So if we're to go back up to our scatter plot, right? Well, look, it only goes to 10. So if we were to draw it way out here, wouldn't even be 20 yet. But if we were to go way out here, then we would expect it to be, somewhere around there. So the idea here is that you can extend this line, because it's just a linear function, as far as you want, mathematically. But it doesn't mean that it's going to make sense, right? First of all, you can't really extend it this way because we're already at 0. You can't play less than 0 hours at something. So even though you could input a negative value, and what would happen is you would get points down here to the left, it doesn't really make any sense. Also, as you continue to go this way, the aggression level scale only goes to 10. So I think I drew the X a little bit low. It'd actually kind of be up here. So you would be, because it's further over on the screen, I just don't have enough room on my screen to draw that many units over. So you would end up with a predicted value that's higher than the scale even goes. If you were to say 30 hours, 40 hours, 50 hours, it's just going to continue the line, and you're going to end up with aggression predictions that go well beyond what the scale actually does. So just because you can work something out mathematically doesn't mean it makes sense. The other issue is that we don't have data way out here. All right, so I'm going to go ahead and kind of erase this here. All right, so there we go. Make this a little bit smaller here. So we don't have any data points that go this far. Our data points leave off at 10. We don't really know much about kids that spend more time than this playing video games. So if you were to make a prediction about somebody playing 20 hours, right, here we go, it would be it's probably a little bit closer, okay? You don't have any information about kids between here and here in this range. So we can't really with confidence say what would happen out here. We didn't sample anyone that spent this much time playing violent video games. So when you make predictions, you want to make sure you make predictions that are more or less within the range of predicted values, range of observed values you have to work with. And you want to make sure that the new predictions you're making are consistent with the ones you've made before, and nothing's really changing. that they're representative of that population that you were drawing from before. And you want to be mindful that just because something works mathematically doesn't mean it actually works in real life. Right? You could compute values way out here, but they may not actually be reliable. So try to keep it within the range of the data you've already collected. Okay, well, let's go back down here. And let's see here. So we're down here to the conclusion. Zoom in here a little bit here, read this better. Based on the analyses above, what can we say about the time spent playing violent video games in children's aggression? Now before it asked us pointedly, did we prove that video games cause aggression? And there were two problems with that statement. First of all, the word prove. We want to be very cautious about how we use that. We're making inferences. We're not necessarily proving things. The other problem is that we don't have any causal mechanisms here. This is a correlational study. We don't have anything to make causal inferences. So let's address that in our write-up. So all we know based on the data is that video game use predicts aggression, and we know the nature and strength of that relationship. Based on our analyses, we can say that time spent playing violent video games predicts children's aggressive behavior. The more time they spend playing violent video games, the more aggressive they're likely to be. The strength of the association is moderate to strong. And it is statistically, let's see, go ahead and we'll make a note about that statistical significance. Let's put this up here. Significantly predicts. Let's put that in there. So based on our analyses, we can say that time spent playing violent video games significantly predicts children's aggressive behavior. When we don't qualify significantly by saying statistically significantly, that's what we're implying when we're doing statistical write-up. Right? So you can differentiate between statistical and practical significance. When you don't qualify it, we're assuming you're talking about statistical significance. So when you say this, what you're implying to your reader is that P is less than 0.05. P is less than 0.05, statistical significance. The more time they spend playing violent video games, the more aggressive they're likely to be. So here we're talking about the direction of the relationship. It's a direct rather than an inverse correlation. The strength of the association is moderate to strong. So here we're talking about the substantive significance of the results. We can even be more precise, can't we? With video game use predicting 24%, I believe it was, the variation. Let's check our R squared. That's where we get that from. Right here, 24%, which is just the correlation times itself, predicting 24% of the variation in children's aggression. That's what we can say about this relationship. Now, we cannot say that this causes this. Let's make that explicitly clear. Because this was a correlational study, and because we did not manipulate the independent variable, we cannot say that video game use necessarily causes aggression. However, the two are associated. I'll say positively associated. So we're trying to make this clear. Here's the relationship we observed. Here's the nature and strength of that relationship, the significance of that relationship. But to be clear, we have not proven that this is a causal relationship. Now that leads us into our final question. It says, if we wanted to make a causal claim about these variables, what can we do? Well, the key about causality, the key is whether or not we've manipulated the independent variable. We've used an experimental design. The whole point of experiments is to make causal claims. Oftentimes, it's easier to do a study, just to collect data, ask survey questions, or we collect existing data. Sometimes it's easier to do that because you don't have to get people into a laboratory and do things to them. But again, the downside is it's much harder to make causal inferences. There's some ways you can go about it. I won't get into that in this video, but there are some ways to go about it. But the most direct way and the most popular way, the gold standard, is to run a true experiment. where you assign people to conditions and you manipulate some variable to see what the result is. You leave everything else the same, you change maybe one thing, or you systematically change some number of things to look and see what the outcome is. So that's what we would need to do to best make a causal claim about these two variables. To best make a causal claim, we would need to experimentally manipulate the independent variable, which is time spent playing violent video games, and then observe the effect on the dependent variable, which is aggression. In other words, we would randomly assign different children to spend different amounts of time playing video games, and then see if they differed in their aggression levels afterward, right? So what would that look like, right? We could actually create an experiment to do this. Okay. You could have 3 different groups. You could have a control group that has 0 hours of video games, and then you could have an experimental group that maybe plays 5 hours, and then you could have an experimental group that played 10 hours. So a couple different treatment groups and a control group. And then you could, after you had them play some number of hours of video games, then you could measure their level of aggression and see how those levels of aggression compared. And as long as the people in these conditions were otherwise similar and you didn't change anything else, then you would be able to say with much more confidence the amount of time they spent playing these video games produced or caused this different result in the outcome. Okay, well, hopefully this was helpful to you to get a sense for correlation, regression, how these concepts are connected, what we can make from correlational data in terms of inferences and implications. And hopefully this has been helpful to your learning and understanding. Thank you.